Hello again. So we got started yesterday on infinite games as the first part of the series about synthesis. And we were looking at the game theoretic formulation of the synthesis problem. So we're interested in building a component that receives an infinite sequence of inputs from the environment and that produces an infinite sequence of outputs. We want to build the component in such a way that temporal specification is satisfied. Now, the game theoretic formulation of the problem sees this as a game where the two players represent the environment and the system respectively, and they take turns in producing inputs and outputs, right? So player 0 produces outputs, player 1 produces input. And if the resulting play satisfies the specification, then we say that player 0, the system, has won the game. And now we're interested in finding a winning strategy for player 0, which constitutes an implementation of the specification. Now we got started with a really simple type of game, reachability games, where the objective is simply to reach a designated set of goal states. And what we saw was that this can be done with a fixed point construction that classifies the states according to the number of steps it takes player 0 to enforce a visit to the goal states. So the goal states would be in this inner set, say with distance 0. Then you go one step back where either the state is owned by player 0 and there is an edge to this set, or the state is owned by the opponent, by player 1, and all edges lead to the set. And so in this example, we got V3 and then and the V8, because they all have just one step into the goal states, then V7, and finally V6. Now, as the last type of games, we started to look into parity games. Parity games have the vertices, the states annotated with colors. So colors are natural numbers, and player 0 wins a play if the highest color that is seen infinitely often happens to be even. So in this example, a winning strategy for player 0 would be to cycle down here, right? From V7 we would play to V6. That would create a cycle where you have colors 1 and 2, and 2, the highest color, is even. From V3, there's a winning strategy that simply plays to V6. And even though that color is odd, it doesn't really matter, because in the resulting play, it's only visited once. And then the set of colors that are visited infinitely often, again, has 2 as its highest element. So the play is again won by player 0. Now, what we'll do next is look at one simple algorithm to solve parity games, that is to determine the winning regions of the two players. This algorithm is due to McNaughton, and it's from 93. So the algorithm starts by identifying the highest color that appears in the graph. So let's say these are the states where the highest color appears. Now, if the highest color is actually 0, or if the graph is empty, then we're done, of course, right? If the highest color is 0, then no matter what we do, the highest color that appears infinitely often will be 0, and it will be won by player 0. So this is an easy case where we can immediately terminate. Otherwise, we identify who the player is that would benefit from infinitely many visits to the highest color. So depending on whether this is even or odd, this is player 0 or player 1. Right? So we set I to C modulo 2, so to the number of the player who would win if we would visit these states infinitely often. Okay, and then we get into a loop where we initialize the winning region for the other player. So from now on, the player who wins if we visit the states with the highest color infinitely often is us, and the other player has as approximation of his winning set W1 minus I. So we initialize that to 0. Okay, and now we build a new game by removing from the game we have, first of all states with the highest color, and then also all states where we have an attractor strategy that would allow the player I to force the game into the highest color. So this simplifies the game because we have gotten rid of the highest color. And we should also note that this is indeed, again, a game, right? So we had this requirement that you can't get stuck in a dead end in the game arena. There always needs to be another move available. And by computing the attractor, we make sure that we never take away all the outgoing edges from some state. Because if the state is owned by the other player and all its edges lead into the attractor, well, then that state is itself part of the attractor, right? And if the state is owned by us and there is an edge, then that state is also part of the attractor. So it never happens that we take away all the edges and still leave the state in the game. So now on this resulting game, we recursively call the procedure again. And that gives us a winning region for the resulting, two winning regions for the resulting subgame. Now, if it turns out that in that subgame, it's our opponent, player 1 minus I, who doesn't have a way to win the game. So the entire subgame is won by us. Then we're in a very fortunate position because, we can play inside the subgame, in which case we're fine. It could be that the opponent actually forces us into the attractor for the states with the highest color, because we have taken off those moves. And while we can't force the game into the highest color, it could be that the opponent actually plays in this way. But if the opponent does that infinitely often, then we still win the game because we visit the highest color infinitely often. And if he stops doing that at some point, then we stay in the subgame where we follow our winning strategy. So either way, we win the game, assuming that we win from all the states in the subgame. So then we just return the result. And the opposing player has the winning states that we've collected so far, and we have the rest. Now, otherwise, what we do is we take this set of states where the opponent wins the subgame, and we actually augment it with the attractor from the perspective of the opposing player around it. Why is that? Well, in this area, we actually know that we're losing the game, because we have no way of forcing the game outside the subgame, because we already took away our attractor when we constructed the subgame. So the only player who could force us out of this subgame would be the opposing player. And he has no incentive to do so because he has a winning strategy inside the subgame. So he's actually winning on this subgame, and if he has a way of forcing the game into that subgame, he will certainly do so. So we know that this area is actually won by the opposing player. So what we do is we add these states to the states.
Where does this extra thing come from if you compare to the previous pictures?
Yes?
Where does this extra attractor come from? It cannot come from the piece there that we already know that we win.
Absolutely. So this was the subgame, right? This part to the left of the half circle, right? This was the subgame we already analyzed. But there is the part where the highest color occurs, or where we have a attractor strategy into the highest color. And it could be that actually from this region, the opposing player has an attractor strategy into the subgame, right? So at this point, we're no longer restricting ourselves to the subgame, but we're back in the full game, right? And there, this part might exist. We actually don't know if it exists. It could be empty. The only thing we know for sure is that this red area is not empty, right? Because if it were empty, we would have been in this case. Yeah? So this is also a central weakness of the algorithm, that the only progress we're sure to make is this one state that is in the red area. This is eliminated. We haven't reduced the number of colors or anything, but we have eliminated at least one state. Okay, so we add this newly constructed set of winning states for the opponent to our set W1 minus I, and now we continue with the subgame where this red area and the attractor of it has been eliminated. And with that, we go into the next iteration of the loop. So because in every iteration we eliminate at least one step, eventually we'll get into the situation that the graph has become empty, or that the opponent actually doesn't win anywhere anymore, right? In which case the recursion terminates. So as I said, I mean, it's a nice algorithm, and the steps are easy to verify. It is obviously exponential in the number of colors. So it is certainly not the best algorithm that you might use for solving parity games. But for our purposes, we have established that that parity games can be solved. So in terms of better algorithms, oh yes, please. So, well, I'm trying to understand the question, but let me think about it for a sec. So I think the question was, if we look at this picture, where the highest color is identified, does the algorithm actually ensure in some way that this color is being visited infinitely often? And the answer is no. It depends on what the two players do, whether we ever end up in these states. It could be that the whole game plays out in this area, for example, right? This is entirely possible. What we're doing here is just accounting for the different things that might happen, right? So in case we never enter this, this blue area to the right, then the strategy that we computed for the subgame will be applied, right? But the opposing player could, if he chose to, possibly move into the blue area. The only argument we made is it wouldn't be to his advantage, because if he did that infinitely often, then he would lose the game as well, right? Yes.
Was formulated it as an algorithm for parity games?
Yeah, or some form of Rabin games, yeah.
Okay.
I mean, people usually give credit to McNaughton for the original formulation in the finite state setting, and then Zielonka for the extension to infinite graphs. But it's the same construction, just with transfinite induction, which we don't need here because our graphs are actually finite. Okay, so Orna's comment is that this is actually a proof that that the strategies are memoryless, and to be honest, I purposefully did not discuss this because I was cheating a little bit, and the cheat consists of the fact that we're changing the game a number of times, and we might apply different strategies in the different subgames. And what we actually have to show, if we want to prove your point, is that we can compose that into a single uniform strategy, which can be done, and therefore this establishes that the strategy is memoryless. Okay. Now Orna is going against the Zielonka proof, saying that this already does it. It does not, because this relies on the fact that we have a finite graph, right? And the motivation for Zielonka's construction is that we actually look at infinite games played over infinite graphs as they occur, for example, when you try to complement tree automata, right? And therefore, this wouldn't do the trick. You actually have to go beyond the finite. But don't let that confuse you. It doesn't matter here. So what I wanted to say is that, I mean, there have been exciting developments in terms of algorithms for parity games, and we already discussed that a number of times, that there are also tools, and it's really a different story which algorithm performs well in practice compared to what the theory says. But this year, well, I would say a major sensation happened, and this concerns the ongoing quest to decide whether there might be a polynomial solution to the problem or not. So we still don't know whether a polynomial solution exists, but at Stock this year, a new algorithm came out that solves parity games in quasi-polynomial time. So you still have the number of colors in the exponent, but as a logarithm. So this is well, more expensive than polynomial, but less expensive than exponential. So, and the first result showed this for time and space, for quasi-polynomial time and space, and then quickly there was an improvement to show that you can do this in quasi-polynomial time and polynomial space, and actually that the same principle can, be applied to different types of algorithms. So, so this one is one based on progress measures. This one is close to the original formulation. So this is exciting, and of course, still an open problem if you can do even better. As we'll see, though, for our purposes, it doesn't matter so much because I mean, this whole discussion concerns the complexity in the number of colors. And as we'll see a little bit later, our complexity is already dominated by the number of states. So even if this were to drop to polynomial, the complexity class of the synthesis problem wouldn't change. Nevertheless, of course, it's exciting to have better algorithms. Okay. So this was the short tour of algorithms for infinite games. And now we're moved back to the synthesis problem. And so far we've ignored the question what the specification actually is for which we're synthesizing. Or we just took the winning condition of the game as the specification. Now we'll go back to logical specifications. So starting with the temporal logic, we'll build a game and then solve the game to find an implementation for the logic. Now, first of all, this is important for us because that solves the actual synthesis problem. And second of all, I think it opens a discussion that has played out in verification for a long time. That is, what is the right specification language to use for synthesis? Because obviously there's a trade-off between how declarative and how expressive the specification language is, and how difficult it is to synthesize implementations from it. I could actually go to a programming language, and then I have as a very deterministic specification language, then I would have a very simple synthesis problem. But of course, then me as the specifier would have to do a lot of work that I would be hoping that the synthesis algorithm does for me. On the other hand, if I go further up and have a more declarative specification, then it is to be expected that I get a more difficult synthesis problem. But what that means is, we can look into some interesting issues here. Okay, so the plan here is I want to talk about LTL, then CTL, CTL star, and finally talk a bit about GR1, which is a specification language, actually a sublogic of LTL that has become quite popular. Okay, so you all know what LTL is. I'll also use the lazy notation with the letters this time. So we have next and until, and possibly derived operators eventually and globally. And all this is based on an underlying propositional logic. So, for example, if you remember the example I had at the beginning of yesterday, that you want to build a circuit that you could, of course, express in LTL by saying that you want mutual exclusion to hold. It's never the case that the two grants are given at the same time. And response, so every request is eventually followed by a grant. So now here's the plan. We start with the LTL formula, and we want to decide whether that LTL formula is realizable or not, right? So what we do is we first build a automaton, let's say a non-deterministic Büchi automaton. Then we determinize that automaton that gives us, for example, a deterministic parity automaton. And this deterministic parity automaton can be used to judge if a given play should be considered winning for player 0 or not. We just run it in parallel, if you will, with the actual play. And now in order to define a play, we simply separate the roles of the two players. So the player 0 is selecting the outputs, player 1 is selecting the inputs, and the automaton then evaluates both choices by going to the next state. So this defines a parity game. And well, by knowing who wins the parity game, we know if the specification is realizable or not, because the winning strategy for player 0 can immediately turn into an implementation. Okay, so this is the plan. You might have a few questions about this plan. The first question is, why deterministic automata? We couldn't we just build a non-deterministic automaton and forget about determinization? That would be really convenient because that would avoid an exponential step. Well, the problem with non-deterministic automata is that they actually also have rejecting runs on inputs that are accepted, right? So now the question is, what should we do with that fact? We really don't want to call a strategy losing just because there is a run that is rejecting. Another tempting solution would be to require player 0 to resolve that non-determinism and make sure that we actually pick the accepting run for the play. But it turns out if we would put that task onto player 0, that would put him at an unfair disadvantage because he would have to commit early on how to resolve non-determinism. So here's a simple example. Let's say the specification says that we want to have that eventually globally the current input is the same as the next output, or that infinitely often, so globally eventually, it's the case that the input is false and oh, maybe I didn't say this right. So let me start again. Two options: either eventually we reach a point where the input is true and where the input is always true and the next output is always true, or we infinitely often reach a point where the input is false and the output in the next step is also false. So obviously player 0 has a winning strategy for this. The strategy is to copy the input directly to the output. So if that is the strategy, then if at some point we have that the input is globally true, then the copied output will also be true from that point on. If, on the other hand, there are infinitely many places where the input is false, then because I'm copying the input, well, the output will also be false. So it's trivial to realize this specification. The problem is you don't know with which disjunct you're going to satisfy the specification because that depends on the input, right? The input could either at some point just make I true forever, or keep producing infinitely many false inputs, right? So it's the choice of the environment what's going to happen. But if at some point I force player 0 to say that he's going to win with the left disjunct, then of course the environment will just start playing the right disjunct and vice versa. So putting this choice on to player 0 won't work. What we'll actually do is we'll eliminate the disjunctions from the specification by going to a deterministic automaton, and then neither player has to worry about it. It's the deterministic automaton that deals with it. Now, the other question is, why do we go to parity rather than, for example, use Büchi automata? Well, the answer is not every LTL formula can be translated into a deterministic Büchi automaton. And I believe Javier will talk more about this, right? So just a simple example is that eventually globally P holds is something that you can't express as a deterministic Büchi automaton, simply because, well, if you have a stretch of P's in your word, then at some point the deterministic Büchi automaton will have to reach an accepting state. And when that happens, you could just visit a not P state in your word, and then again a long stretch of P's, right, which would force the automaton to again at some point visit the accepting state, and so forth. So because the run can't depend on the future of the input sequence, you can trick the deterministic Büchi automaton into producing infinitely many visits to accepting states. So this problem is resolved by going to a more expressive condition such as parity. Okay, so let's see what happens in a simple example. So this is like the progress property, but just now for one client to simplify the problem. So let's say whenever a request comes, we eventually want to see a grant. Now here's a deterministic automaton for this. I need two states. The left state says that, well, there is no open request right now, right? So nothing to worry about. The right state says, I've seen a request, but not yet a grant. So I'll wait here until I actually see the grant. So this state gets color 2. So if I visit this one infinitely often, then I'll accept. This one has color 1. So if I ever get stuck here waiting for, having seen a request but not yet a grant, and if this takes forever, then I will reject. Yeah. So you start here, right? You circle while you have either no request or you have a request and a grant, so everything is immediately in order. But if you see a request without a grant, then you go into this waiting state, and you stay here while you're not seeing a grant, right? And as soon as the grant comes, you go back to the state P. So this is the first step. We have taken the formula and translated it into an equivalent deterministic parity automaton. Now we translate this automaton into a game. As I said, the step is simply that we separate the choice of the input and the output, that is the choice of the R and the G, into the two players. So here, let's say we are in this state. It's a state for player 0. So now we choose the output. So the output could be the empty set or the set that contains the G, right? So we either set the grant or we don't do it. And then once we have made that commitment, the player 1 can choose the request. So let's say we have gone here, that is the player 0 has chosen not to give a grant. Then player 1 can either put in a request or not put in a request. If he doesn't put in a request, we're back to where we started. So here you also see the the state of the automaton, right? So we started out in state P. If no grant was given and no request was posed, then we're back in state P. But if no grant was given and a request was posed, then we are in this case that altogether there's a request but no grant, so we move to state Q. And so it goes, right? Once we're in Q, player 0 could choose to not give a grant or to give a grant. If he chooses, while the automaton is in state Q, to not give a grant, then the game will just return to Q, right? It doesn't really matter if player 1 poses another request or not. Either way, we're going to stay in the waiting state. But if he chooses to give a grant, then no matter if there is another request or not, right? If we have a grant and we're in Q, then we'll go back to state P, right? No matter if there's a request or not. So in that case, the game will return to the upper state. So now we have translated the automaton into a game, and we can solve this game. Well, it has a simple solution. For example, I might start out by not giving out a grant. So I go into this state. And if there's a request and I'm in the waiting state, then I might choose to actually give out a grant, which would bring me here, right? So if you do that, then the game will cycle like this. Whenever there's a request, I answer by giving out a grant, and that brings me back to the safe state of the automaton. So this is a winning strategy for the game, and of course I can represent what player 0 is doing as a finite state machine. Namely, I wait while there is no request, but when there is a request, I immediately give out a grant, which means that I get taken back to the original state, right? And from there it continues. If there's a request, I'll answer with a grant and therefore get back to the original state. Okay. So now we know how to solve the synthesis problem for LTL. Let's take a look how expensive that is. Oh, yes. Okay, excellent question. This would be this line, going from the deterministic automaton. The question was, what is the blow-up going from the deterministic parity automaton to the parity game? And if you look back, this was this construction. So you see that every state occurs multiple times in the game because, well, for example, P appears here, and then it appears here and there, because what happens from here to here is that the player 0 chooses the output. So the state hasn't changed yet. We have only changed the output. We need to record what the last output was in addition to what the state is, right? So going from here to there, we multiply the number of states with the number of choices of player 0. So to summarize, I mean, the answer is nothing much happens. It's a polynomial, very low polynomial.
The alphabet is exponential.
If we have to say what the alphabet is Moshe's comment, and of course, if you look at the formula, we have a very succinct representation of the choices, because if you have n inputs, propositions under the control of the environment, then the actual number of choices is exponential in this number. So yes, if you count if you approximate the number of inputs by the length of the formula, then this gives you an exponent. Yeah.
On the left here, you have a transition from Q to P with both request and grant at the same time.
Yep.
Where is that represented on the right?
You mean
Yeah,
this situation that you have request and grant in the same step. This would be here. If I commit to giving a grant, player 1 commits to giving a grant, then even though I see another request, I'm back along this edge to state P. Okay. So, but this issue with the exponential dependency in the inputs is actually a very interesting one that we'll return to tomorrow, probably. I mean, for the purposes of this discussion, we consider the inputs as constant, right? But in reality, that's of course not always the case. In particular, if you build circuits, then you know the number of inputs is exponential in the number of wires, and this is something one needs to deal with.
But it's an artifact of the notation that we chose to have. We chose to have a notion of parity game, which is just completely state-based, no notion of action. There is a simple variation in which the actions are more explicit.
Okay, so Moshe's observation is, you know, we're short selling ourselves by actually having a succinct representation of the input, because you know, every valuation of the input propositions constitutes a separate input. If we wanted to sell ourselves better, we could call every such valuation a separate input, and then of course this would be a polynomial in the inputs, which is implicitly what I've done here. But I disagree with you that that would be a better way of doing things, because I mean, in reality, we want to build circuits, and circuits have this succinct representation.
It would isolate that there is a central problem here, which is the one-step Boolean synthesis problem, which is here. It's kind of we've been push it into the notation. But the reality is, you can imagine that you just want to compute a one-state attractor, right? If you have a very simple formula, just for between this state and the next state. All you have to do is do classical Boolean synthesis.
Yes.
And that's really the building block here, which is kind of been hidden away, but of course it's there.
Okay, so we're getting ahead of ourselves, because I'll get into these issues tomorrow. But I mean, since you're bringing up this really fascinating discussion, you know, both in verification and in synthesis, there's always the choice between explicit solutions and symbolic solutions. And explaining a explicit solution is of course way easier. And if you go the explicit route, then you don't want really to worry about the compact representation, say, of an input in the formula. Likewise, you don't worry about, you know, how much space it actually takes to represent these states, because there's a much better symbolic representation than the explicit representation that I'm drawing here. But I mean, if I would give you all this in a symbolic fashion, then nobody would understand what's going on, because I would, you know, I would not have 4 states, but rather I would have 2 variables that encode what's going on. So therefore, for the purposes of exhibition, I mean, this explicit discussion is much more helpful. However, if you actually build a synthesis algorithm, this is total garbage, because you do want to be symbolic whenever you can. And therefore, we will have to return to that issue when we actually talk about practical algorithms. But for now, let's stay here. Okay. All right. So we were talking about the complexity of this. So the translation from LTL to Büchi automata creates an exponential number of states. Then the translation from non-deterministic Büchi automata to deterministic parity automata again has an exponential blow-up, meaning that we get a doubly exponential number of states, and now we get an exponential number of colors, because the number of colors is determined by the number of states of the Büchi automaton. Now the construction of the parity game, as we discussed, is actually not that expensive if we ignore the input issue for now. So in the end, we get something that is a parity game that is that has doubly exponentially many states and exponentially many colors. Now, we know that we can solve this in polynomial time in the number of states and less than exponential time in the number of colors. So overall, we can solve the problem in a doubly exponential time. Okay. So now the next step is to move from LTL to branching time. So CTL star, you've seen multiple times. We have state formulas and path formulas. The state formulas have now existential and universal path quantifiers. The path formulas are essentially LTL formulas whose, instead of propositions, you may have arbitrary state formulas. Now, in order to get now to a game, we have a little bit more work to do. And what I want to do is use tree automata as an intermediate step. So we'll look at the strategy trees. You remember a strategy is a function that maps finite histories to successor states. And we can depict that by a tree that is labeled with the values of the strategy and that branches according to the possible inputs. So we'll label the root with the strategy for the empty history. And then we have two choices. Let's say we just have a single input variable I. Then we have as input either the empty set or the set containing I. And then we'll label the successor, well, with the value of the strategy for the history that consists of this one step, right? So here, for the history consisting of just one step with the empty sequence, here the history consisting of one step with I, right? And so it continues, right? So down here we have the history consisting of I and then the empty set. So we label this node with the value of the strategy for this history. Here we had two I's, so we label this node with the value of the strategy for the history II, and so forth. So this creates an infinite tree that represents our strategy. Okay, now we'll go from the CTL star formula to a tree automaton, accepting all the trees, all the strategy trees that would satisfy the CTL star specification. And now at that point, we have a representation of all possible solutions. And we need to find out if the language of this tree automaton is empty or not. That is, if there exists one such strategy tree that would satisfy the CTL star specification. And it turns out we're fortunate in that the emptiness of a tree automaton can again be decided using a game. So this is called the emptiness game of the tree automaton, and we extract that game from the tree automaton, solve the emptiness game, and then are in the same situation as before. That is, if player 0 wins, then we know that the language was non-empty, and therefore the specification must have been realizable. If player 1 wins, then we know that the language of this automaton is empty. There doesn't exist a strategy tree that would satisfy the CTL star specification, and therefore the specification is unrealizable. Yes, please.
So what are the pros and cons to use LTO or CTL star to do this? Since LTO is a subset of CTL star, right? So if we have a CTL star, then why do we need LTO?
So the question was, apparently you can do LTL and CTL star, and CTL star is more expressive than LTL, then why even bother with LTL? Good question. I mean, we'll get more into it, but the asymptotic complexity of the two languages is indeed the same, which, by the way, is the same situation as in verification. That asymptotically, CTL star doesn't make the problem any more difficult than LTL. I guess the simple answer is that taking care of all this has a little bit of conceptual overhead that you want to avoid if all your specifications are in LTL. But in principle, there is no reason to restrict yourself here. Do you agree, Moshe?
From a theoretical basis, yes. From a practical point of view, CTL star was always an academic language in LTL, and it has been industrial conceptually thinking about traces is much more intuitive than trying to think about traces.
Yeah. So Moshe's answer was more or less the same I said. I think in that for theoretically there's no difference, but in practice people have argued that you really don't need CTL star, that LTL is much more intuitive and therefore is all you need. It's arguable if, yes please.
So just to say, this is what, when I was a freshman student.
Hold on.
When I was a freshman student in physics, one of the graduate TA told us something very important. He asked us, what is the difference between theory and practice? And we couldn't come up with a good answer, and he said, in theory, they're not very different, but in practice, they're very different.
Thank you. But actually, I think this is a discussion that we should be having. Maybe right now is a little bit early for that, but when we are at the end of this part.
Or this afternoon in the industrial panel.
Okay. Because I think there may be a difference between verification and synthesis here. Because you see, in the synthesis problem, the environment is always unrestricted. We force it to produce all possible inputs, and therefore LTL indeed can make sure that no matter what input comes in, nothing bad happens, right? But this is sort of one-sided from the point of view of the system. Maybe you're interested in what the environment can actually achieve, right? So, and for that type of property, you know, if you want to argue from the point of view of the user of a system, that it might be that there are actually important properties for that are in branching time. But indeed, this is a longer discussion.
But if I can have one more comment. In the linear time case, it's very clear in some sense that what the game is. That we have a very clear game. The environment does something, and the system does something, and then we have essentially one universal quantifier over all the branches. It's less clear if you talk about CTL star synthesis. Essentially, what this is really CTL star satisfiability. It just builds a model for CTL star formula. But if you're really trying to think about like something like CTL star synthesis, you have to start thinking much more carefully about the interaction between the players and the quantifiers. When you say something exists, what does it mean exactly exists? Is it because we have two adversaries? And again, CTL and CTL star kind of ignore this issue, where do quantifiers come from? And you take a more refined approach, and you can add actually, there are some version of CTL star synthesis where it's going to go to higher exponential, beyond doubly exponential. So the picture gets more complicated. This is a simplistic CTL star synthesis, I would call it.
Okay. Before we decide if this is simple or not, at least let's take a look what it actually does. Well, I think what I can do at least is tell you what a tree automaton is. Can I ask who's familiar with tree automata? Tree automata over infinite trees? Ah, okay, this is not so bad, so I have a fighting chance in the remaining time. So a tree automaton looks quite similar to the word automata that we have been concerned with. So we have a finite number of states, we have an initial state, we have a set of transitions, and then we have an acceptance condition, which in the case of parity tree automata is again a labeling of the states with natural numbers. Now the interesting difference is in the set of transitions. So what we have here is a relation from states and symbols to a function from directions to states. So that means if you are in some state of a tree and you observe a certain label of that state, then you have to give multiple successor states depending on the different directions your tree branches into. Right? Each direction may branch into a separate state. I'll show you an example in a moment. So a run of the tree automaton is again a tree, namely an annotation of the given tree with states of the tree automaton that corresponds to this transition relation. And the tree is accepted if on every path, right? The tree has multiple paths, of course, and on every path we need to have the acceptance condition to be satisfied. In the case of parity, the highest color that appears infinitely often needs to be even. So let's try this out. What I want to look at is a simple existential response property. So it's always the case that when the request comes, then there exists a path where eventually there's a grant. So quite similar to what we did before, right? Before we said that on every path, whenever there's a request, there will eventually be a grant. Here I'm saying that on every state on every node in the tree, if there is an R, then well, there is a path where I will see a G. So as before, I will use two states, P and Q. And again, P will mean that there is no open request that I want to worry about. And Q means that now I have seen a request and I wait for a grant. Now I'm going to look at a tree. This is a strategy tree, right? And this means that I start out by not giving a grant. And if there's no request, I'll also give no grant. If there's a request, I'm lazy in this example and I don't give out a grant either. But after the second request here, I decided to give out a grant, right? So you see what's going on. I'm branching according to the possible inputs, and the nodes of the tree are labeled with the outputs chosen by my strategy. So now I need an initial state. Well, I'll start out by not waiting for a grant because I haven't seen a request yet. And therefore, I'll label the root of the tree with P. I always label it with the initial state. Now, from there, I need transitions. And in this case, I need a transition that tells me what happens if I'm in state P of the automaton. I observe the empty output, that is no grant, and now I either see no request or I see request. In other words, how should I proceed if the situation occurs where there's no request? How should I proceed if there's the situation that there is a request? Well, I'll say that if I'm in state P, I observe the empty output. Then if the input is also empty, then I'll stay in P. And if the input is the request, then I'll go to Q. That is, I'll start waiting for the grant, right? Correspondingly, in the tree, I'll label the successor along the direction of having an empty input with P, and the successor that sees a request with Q. Okay, now here we're again in the situation that we're in state P and we're observing that there is no grant given out. So this is also covered by our first transition. So we'll do the same thing again and label this successor with P, this successor with Q, right? The empty direction goes to P, the R direction goes to Q. Now, what about, where am I? This situation down here. So I have reached a P, and now I see a grant, right? So the first transition governed the case where there was no grant. Now I see a grant. Well, when that happens, I don't need to worry, right? I have already my grant. Therefore, I stay in P in both directions. So this is what this transition says. If you see a grant, then and you're in P, then stay in P. Don't worry, right? Nothing to do. Okay, and so it continues. Here we are in Q. That is, we're waiting for a grant. If we're waiting for a grant, then when we don't see a grant immediately, then we should keep waiting. But since this is an existential property, we only need to find some path where the grant appears. So in principle, I could expect to find it on the left, or I could expect to find it on the right. Now in this example, I have chosen to expect it on the right, right? So I have sent the tree automaton to P along the left side and to Q along the R side. Now, really, there is no big alternative to this because here there's a new request, so I need to find another grant along this direction anyhow. But if I want to say that the grant that covers this request is somewhere to the left, and the grant that corresponds to this request is somewhere to the right, then I could use this transition that simply sends both directions to Q. In that case, I expect to find a grant along both directions. So for example, I've done this here. So meaning the tree automaton is non-deterministic. There can be two transitions that are applicable. And here I have sent both directions to Q, which doesn't do much harm because there's a grant anyhow. So I will return back to P immediately. Okay, so now the last case is that I'm in Q and I see a grant. Well, this is here, for example. In that case, I have fulfilled my obligation and I go back to P. So you see how in this fashion we label the tree with states of the tree automaton, and now the acceptance condition gives me a color for each state, so I can look at all the paths in the tree and determine if the highest color that appears infinitely often is even or not. So for example, if I look along this path, I see only P's. P's have color 2, therefore the highest color that appears infinitely often is even, and this path is okay. Now obviously, since I've only shown you a finite part of the tree, we can't really say whether the tree will be accepted or not, but you see the pattern. Okay, so I think I'll unfortunately stop here. What we'll do then tomorrow is see how we can represent the decision whether such an annotation exists that satisfies the acceptance condition into a game. So the idea is going to be that player 0 not only chooses the outputs in our tree, that is the strategy, but also the rest of the transition of the tree automaton. So it not only says, what am I going to output, also why is this justified? Which transition of the tree automaton justifies that this was correct? Okay, but more about this tomorrow. Thank you.